Okay, a very good morning, and I must say I'm very excited, seeing lots of energy and very enthusiastic to come here and speak about it. I'll give a quick introduction about myself. I am Deepak Mahto. I have spent a decade in databases. Before joining Google Cloud, I was working for Amazon AWS, and I spent a considerable time on databases. So I like to call myself as a database guy. And there are different things of AlloyDB that I want to pitch in for today. And we are in a phase where there are things that happen a lot on databases, and there are no SQL and a lot of things, but we have the main agenda that I want to cover today is how the database has evolved, what are different things that we can do as of today in databases world as well. So let's walk through it. Okay, so this is the agenda that I want to cover for today. At the end of the section, there's a new service that we have recently launched, which is Omni. I like to take that, give you away that on, and something to try on after this session. Okay. Now to start with, can anyone guess how many number of databases, relational database we have as of today? Any guess number, like anything? Thousands, okay, that's a very high number. So currently, officially, we have 897 relational databases, and it is still getting released every year and day by day. So it's not that the database is as a backfront as part of NoSQL. There are lots of things happening as part of databases. Now, in databases world, when I started, there was a lot of cases where I run something as a query. Let's take this an example as an article query. You run it, and you wait for the response. Does it happen for a lot of folks? I assume yes. OK. And I know we are very meme-friendly. I've seen lots of tweets around GDG when it was happening. So see, once your database is slow, it's something that it's stuck, right? It doesn't add any business value. You have to do a lot of stuff to come out of it. Now, when we talk about the use case, over here, just think about it. If you want to do analytics on databases, you do aggregations. When I talk about aggregation, it can be doing a count, min, max, understanding what was the revenue for last day, a year, and so. And when we talk about databases, we don't relate database with analytics. A database is linked to transactions, which is something in ACID compliant. But for today, we'll see a new era of databases where we try to combine the stuff and try to answer a lot of business questions that we have. Now, as Prashant walked through a different evaluation, as part of data, we are also have gone through an evaluation. So if you see at the slide, the value proposition or the high value that a customer were looking for in the past was what has happened, which talk about batch analytics, which means that I have historical data, I need to analyze and get a value out of it. Currently, we are in an era from last 2 years and future where we're looking at what is happening, and which in technical terms, we call it as real-time analytics. And as we are in the phase 23, is 2023, AI is something that I think even my parents are talking about it. So it's a phase that we all are going through. And in future, it will be where you will see a contingent intelligence that is coming in as part of it, which says that what might happen. Now, as I was talking about databases, I talk about transaction analytical. There's a term that you can relate to it, so which is called as HTAP, which is hybrid transaction analytical processing. So as the terminology says, it is combining analytics with databases. At the same time, we at Google Cloud has a vision to bring something which is open, unified, flexible, give a real-time value. At the same time, it's very performant. So the term for the database that we use that use both transaction and analytical is HTAP. So AlloyDB databases that we have in Google Cloud is under the HTAP category. And over here, how many of you have heard about an open source database, Postgres? OK, I think that's a very, I didn't expect that much of folks raising hand. See, Postgres is all about a very strong community. And we all coming here together itself is an example of a very strong community that every technology has. Postgres also have a very strong community and technology which come forward, build an open source software, add in very high-end features, and keep on releasing it. If we talk about today's database era, a lot of cloud are using an open source like Postgres as a platform and then forking and adding re-engineering stuff into it to make it more performant. So Postgres is something which is used across cloud, be it Amazon, be it Azure, be it Google Cloud. It is used across cloud. And we at Google Cloud has invested heavily on PostgreSQL. Over here, does anyone knows the meaning of Alloy as itself? Anyone to try what's the meaning of Alloy? Okay. So it's basically combining two metals and generating a metal or creating a metal which is more strength, has more resistance towards corrosion. And that's what AlloyDB is all about. It's like getting the best of PostgreSQL, getting the best of cloud native, getting the best of engineering, and combining all of those together with an intelligence within the database itself, which I will talk about what's the intelligent portion of it. And all of this combined together is something which AlloyDB comes with. So in precise, get the best of PostgreSQL, which is one of the top used relational open source database that we have as of now. Combine it with the engineering that we have at Google in terms of all the technology that we have as part of a cloud native, and bring as part of databases. So these are some of the performance metrics that I want to just share across. Now, when we talk about re-engineering and the way the database has evolved, there's a need to be highly performant, not in terms of analytics purely, but also in transactions. So this is an official number where we claim that it is 4 times faster than vanilla Postgres in terms of supporting transaction workload. And the next slide is something that I'm always very excited about to talk to, which is the capability to solve an analytical problem for the data that reside within the database itself. So currently, a traditional database have a format in which they store. If you want to guess, it is a typical row format. You have a table, you have a row. But with new era, there's a combination called as hybrid, where we can also store columnar data. And because of that, we have accelerated the overall performance. So for an analytical query, if you want to do on AlloyDB, which provide a hybrid environment where we can have row and column both, you can get an accelerated performance. So for demo, I have some of the sections which cover this, where some of the queries are taking time which does not use this technology, and some of the queries that use this technology, we can see how performant it is. Now, as part of combining all of those together, right, when we talk about databases, we always talk about availability, how scalable it is, and also with the AI/ML portion, how intelligent it is, at the same time performant. Right? There's a very interesting code as everything fails every time. So you have to plan your architecture in a way that it is highly available. So currently, the SLA that AlloyDB has is 99.99% of SLA, including maintenance. Why I'm emphasizing on maintenance? Because database always has to be maintained in terms of upgrading a minor version, security patch, and all of those. Does anybody can guess what is 99.99% SLA actually means? It's uptime, yeah. And if it is 99.99, how much is the downtime that you can get? So it is 8 seconds per day. And if I take that cumulative 2 years, it's only 54 minutes of downtime that we guarantee with SLA of 4 nines. And this includes maintenance as well. So that's the differentiation that we bring with our databases, which is AlloyDB, as compared to the other databases that we have. At the same time, being intelligent is something that is not like a good to have, but a need to have feature. So database itself is intelligent to manage its own memory. I'll talk more on another slide, but the key idea is a database itself has to be intelligent in terms of managing its own properties, its own configuration, and being performant at all the load. And finally, performance, that I already talked about. Now, this is a unified view of all of our database offering that we have in Google Cloud. AlloyDB is something new in the town, which got released last year, and you see that it is fitting in Google Cloud native, but in relational family. So if anyone asks what is AlloyDB for Postgres, it's a transactional relational database, sub-analytical query, re-engineered so cloud native databases, and performant with the SLAs that we talk about. Also, there are some of the services that you will see a common at the bottom. Does anyone have you heard of data stream, data migration service? Can I get a raise hand who have heard about DMS or data stream? Okay, so it's a facilitated service that allows us to migrate databases onto cloud. And these are services that help you to get your databases on cloud from any other cloud or from your on-prem. Okay, now some of the key advantages that AlloyDB bring in as part of being differentiated in database. A very important concept of being performant and at the same time having a reduction in point of failure, which is being fault tolerant, is disaggregation. So cloud computing is all about compute and storage. In initial revolution that we had, as Prashant was walking through, there was a trend to have compute and storage in a single unit where it can fail. A failure was not categorized as a compute failure or a storage failure. But with disaggregation, you can always categorize it. So AlloyDB has a feature where there's a distinguished disaggregation between compute and storage. A very simple example will be that in case a YouTube video got viral, does the person who has uploaded a video need to do anything to support the load that he or she is getting as part of that video to adding millions of views? This all need to happen implicitly, right? So that need an intelligent storage and compute to manage the workload based on the usage for that particular service. And that's what disaggregation of compute and storage bring in. As and when the load increases, storage will scale as itself, manage the load, and same goes to compute as well. Now, this is some of the distinguished terminology that I just want to pass it on. As part of databases, you might have heard about instance, tables, and all of those. When we talk about AlloyDB, we have cluster, and we have multiple instances. So the key takeaway from here is, as part of instances, you can create at least 20 read pool instances as part of AlloyDB at max. And the best part is, all of those compute can have different configuration. So you can have one compute which is 4 vCPU and 16 GB RAM, or 32 GB. You can have one compute which is 2 vCPU. So the idea is, you have a storage, which is ACID compliant and all of those, but also you can vary the compute. So I'll show this in my setup that I have. And that's what make it very differentiated in terms of cluster. And also, as part of databases, we have to be aware that currently, databases are meant to serve two purposes. In a very simple term, it is read and writes. So primary instance, as you can see on the slide, this serves the write portion of it. Only primary can serve the writes, and you can do read from any other instance. Now, this is very interesting slide that go in more depth about AlloyDB. So some of the terms that you see on the slide, one is RPO, failover replica, read pool, and all of those that is you can see on the slide. The key idea I want to pass on with this slide is, whenever a failover happen or there's an availability zone failure, the failback or the instance is always up and running. We will see that in demo. So you'll always have a standby zone where you have that instance up and running, which guarantee that whatever commit happened is persisted even if there was a failure. And that's what any database on a cloud need to guarantee as part of RPO being 0. So that's what that RPO 0 means. It means that if my commit happened, and if a failover happened, I'll always see that data. Now, this is the intelligent portion, right? So when we talk about databases, there are lots of stuff that you want to do automatically. And you don't want end customer, end user to do it every time. So when I started my database journey a decade before, we need to do each and every parameter configuration before provisioning databases. But nowadays is a single service that API that you have to invoke, and it try to manage automatically of it. So when we talk about databases, it basically try to do vacuum management, which is a typical part of Postgres as part of handling MVCC. I won't go in more on depth, but this is an important process that you need to run. Then a memory management means that if your workload increase, you auto-manage that memory for databases. You don't have to do that manually. And also auto data colonization, which I'll talk more depth in the next slide. And this is our the highly available and reliable slide, which I talk about the 99.99 SLA, right? So, which means that your database has to be available across zone. If a failure happens, it should be available, highly available, and adhered to an SLA. Because database serves a lot of critical portion. So we are in a BSc building, right? So we all know the criticality of a single transaction that you do for trading. If your asset compliance is not guaranteed for a failover, it can impose a lot of business loss or credibility as part of not being serving those transactions, right? So it becomes a very high stake SLA that we have to adhere when we talk about databases. This is, again, an interesting piece that AlloyDB bring in. So now, bringing a databases and not integrating with AI, it's something, it doesn't have a USP on AI front, right? Now, what it does is, let's assume that you're doing a transactions, and you want to categorize, suppose you're doing a refund transaction, and you want to categorize that, does the refund is fraudulent, or it is because of false claim, and you want to do as and when you're doing that transaction, this integration allowed to do it. So we can integrate ML Predict Vertex AI pre-trained model with AlloyDB, and you can call that as and when you're processing a database, as and when you're doing a transactions. And that's what the intelligent layer comes in. So it gives you that flexibility to integrate with Vertex AI and call as part of the transaction processing that you're doing. Okay, so moving to the next section is the analytical portion. Now, if I talk about row and columnar format, this is a very simplified diagram that try to distinguish both of them. Now, when we talk about a typical row format, in case you have 4 columns, you will segregate that in a row one after another. If there's a column, it is basically vertically, as you can see, it is trying to group all of those together. And that's the core differentiation that we see when we talk about row and column format. So if I want to access column 1 in a row format, I need to read the whole row. But if I need to access only a column, I'll just read that particular column, not the complete row. That's the distinguish that it brings. Now, as part of AlloyDB, what it has done is, it has combined. Now, let me give you a scenario that you can visualize. You have an analytics running, and at the same time, some transaction is also happening on those tables. Which means that if your analytical query was returning 1,000 rows, and someone inserted a couple of rows, your analytical query should return 1,002. So that has to be consistent with the analytics result. And this is what we are trying to solve by making it as hybrid, which means that the analytical result from columnar storage will be always consistent with the transaction that we do, and hence the real time. So there will be one system which is primary, doing all the transactions. There will be one system which will reading and processing columnar query, that is analytics, and you will see a demo around this as well. So the idea is, as and when the transaction happen, I want to include those as part of my analytics, so that the result that analytics query give is consistent and it's real time. And there are lots of caching also in place, which I won't go in depth, but we have added a cache. So in database world, the biggest performance issue is reading from storage. So if you do an I/O and directly read from disk, that's the highest bandwidth and latency processing that need to be done. But with caching layer that we have, it try to reduce that portion as well. And finally, the very interesting piece. Now, what if I tell you that all the features that I explained, you can get it on your laptop? You don't have to provision a machine on a computer. And that's where the Omni is trying to solve. So if you remember Prashant's slide, there was a future trend where we talk about edge computing, sovereign, and all of those factors. And that's what we are trying to solve with AlloyDB Omni. What it means that you can get the best of AlloyDB, all the features, Not all, but most of the features that we talk about, and you can host it as and when wherever you want it as part of Postgres compatible. So we can host it across multi-cloud, on a Linux compute laptop, on a edge computing and different platform. So this is something that will give anyone an opportunity to try out, and this is available in preview for everyone to test out. So this is a basic screenshot of a containerized AlloyDB that I'm running on one of the instances. So it is running beneath a Docker instance and Docker containerized, and where we have a couple of services running, and AlloyDB, this is on local. Local on the sense it is on a compute, not on a managed service. And this is the URL that you can scan, and it will give you the link that is an official Google Cloud AlloyDB Omni link, where you can download and try to test it out on your own compute and get all the features that I talk about, which is HTAP database, highly performant, article improvement, also Bing serving the transactional query as well. OK, I have some more slides, but we'll go to the demo. OK. So let me quickly go to the demo. Hope this font is good. OK, so before that, so whatever I've told in the slide, I just want you to see over in this section as well. So currently, we talk about cluster. We talk about primary. So if you look at the primary instance, it is 4 vCPU, 32 gig for me. I have one more read pool instance, which is of same size. But I have some other instance, which is of different size. See. And all of this can work on a single storage. So can anyone observe what's the core difference at the storage use section of this view? Can you see the difference in storage use across rows? The storage use is attached to cluster, but not to the instance. And that's the disaggregation I was talking about. So it is attached to the cluster, but not to the instance. And in that way, we can have different types of instance in terms of configuration, but of different size. But we need one primary where you can serve your read and write. And others are only purely read. So this is the configuration that we'll see in our demo. So we have a primary instance, a columnar engine instance. The name itself implies that it is the instance where we have enabled the analytical feature, the columnar engine feature. OK. So I'm pretty old school, so I'll go to terminal, but not a fancy application. So just leave with that. So I'm connected to databases. So I'll quickly connect to my columnar instance. So let's assume that you connected to a columnar instance. I'll do the same. I'll connect to my primary instance. So there are two instances that I've connected to. I'll run an article query on one of the instances. So it is running an article query, doing some count star, and doing some filter. So as you can see, it is still taking time to return, right? It is still running. And if I go back and run this query over here, it responded back. And it was in a less than second, 300 millisecond, right? And if I go back to the other instance, it took close to 20 seconds or more. I can have a demo where I can keep it running, but for the demo sake, that's the difference I want to show. And also, one of the pieces that we see over here is, that I want to show you over here is, at the read pool section, we call it as read pool, and there are a number of nodes that are attached to it. So if you see at this read pool, how many nodes are attached to it? And if I look at this read pool, how many nodes are attached to it? So that means that we have two machines attached to that read pool, and one machine attached to this. Now there's a concept where you call it as horizontal scaling. Thus everyone is aware of that term, horizontal scaling, which means that as and when you increase the compute, based on linear regression, you should also increase the output or the transaction per second that it processes. Now let's look at that in action. So what I'll do is I'll connect to both the node, do some benchmark that will do some queries, and let's see the output that it's producing. So I'll again go to my So over here, I'm running some benchmark on my one of the read pool. I'll do the same for other. Hope demo god is with me, so it should. So as you can see, I'm doing some of the transactions. Over here, TPS is the queries in terms of select. So I'm doing select, and I'm producing a result. So if you can see, it is doing 8K query per second for that particular instance. So the total query that it was able to process was 8K. If I see in this, what difference do you see? Do you see a difference in TPS? So if I just show this screen, you had 8K of TPS that happened, but what about this? So what this implies is, as part of adding more compute, I was scaling my reads, and that happened horizontally. If I make it 4, it will be more than this. So that gives you a power of, in AlloyDB, where you can scale your reads. And when I talk about reads, it's all about doing analytics and other processing. Okay, now let's move to the next section. Now this is a pure HTAP demo that I want to show, which means that primary will have some transaction that will happen, and columnar engine or the other node will give you an analytical output. Now before that, I'll just quickly revisit the columnar part. And just remember this number in mind for now. Okay, and we are doing a count on columnar, and this is the number. Now what I'll do is, like, I'll go to primary. I'm doing the same benchmark, but the difference is this time I'm doing all the DMLs. Insert, update, delete, so I'm creating record. So I'll go to a good fancy other one. Okay, let me just do. So this screen is a refresh screen. So it will, if you see the time, it is keep on updating and giving a count, right? So the count is constant, but time is increasing, which means that it is getting refreshed automatically. Now let me go back over here and start the bench. So I'm simulating a workload where we are doing some changes at a real time. So you can see the transaction happen. And this transaction is pure DML. So I'm doing 4K transaction per second on a set of tables. And if you look at the queries count, does it change? And that change happened because of the transaction we are doing. And that's where it's HTAP in pure sense. And you can see the result. It is not taking much time to come out, right? It is getting a refresh as and when I'm doing. So interval is 1 second, it is getting refreshed. And that's the differentiation we want to bring as part of database world, where you can do analytics at a scale, which is real-time performant, also a transaction system which is performant on its own. So internally, there's a concept called as columnar store. So every table, the table that I was running, it has some of the columnar memory. So if I just show you in a very good view over here, it has some memory portion that is in columnar, and it also have some, just give me. So this particular set of columns were added in that columnar memory which I was talking about. And it is not in, it's a kind of in RAM, but it's not a cache, it's a store. So difference between cache and store is, any cache will have, does everyone is aware of LRU algorithm, least recently used? As and when that algorithm kick in, it will take the portion out of memory. But this columnar store does not work in that way. So it is a store, it's not a cache. So it is persisted over there, but it gets refreshed automatically. And that's what happens. So you get a hybrid environment where you do, so DML does not happen to columnar store. In any databases, DML will happen to row, and your columnar data get refreshed. So that's the difference over here. So this is, before the demo, I've already added the columns and everything on columnar store. Hence, you're seeing the difference. Okay, now, I talk a lot about high availability, right? So let's see that in action, how it actually behaves. So let's assume this terminal to be an application. Okay, so what I'll do is, like, I'll use the same thing. So this is my primary. You see the time keep on updating, which says that, let's assume it to be heartbeat. If my heartbeat is kicking in,
I'm alive, right? So that's what it is trying to say. And I'll also have a similar heartbeat for other instance. And let's kick in one more. So these are some of the compute that I'm connecting to. I'm doing an SSH into it. Cool. Now, you see there are three systems which are active. One is analytical system, one is reader, one is transaction, right? Now, let me go back to the screen. Can you see there are two instance zone that it is specifying? So one is your primary, other one is your standby. Now what I'll do is like I'll manually trigger a failover that will cause a failure. And also notice that we have an application which is doing some work over here, right? So I have done three different applications. So if you see the time is changing, okay, in all of three. And let me just create a do a failover over here. So it will start the failover, which means that there should be a switch between this. Your 1F should become primary and 1C becomes standby. That's what the failover happened. Your AZ should switch. If I go over here, can you see the time is still increasing? If I go over here, do you see the time is paused? And there's a red that comes that says that here. But on other node, you don't see that behavior. Your columnar or other one, you don't see behavior. But on primary, you see that connection fail. This is because we trigger a failover. So the point I want to pass on is, your read can still be available, though the primary is going through failover. And after some time, automatically that switchover will happen. We don't have to do anything. So if I go over here and do a refresh, so I'm just doing a page refresh. Everything happened beneath. So you'll see a switch over here. Initially it was C, now it is F. F is the zone, and this is again up and running. And that's how high availability is defined in a real case. And just final 1 minute, so I won't take much time. I just want to show you the Omni part. Okay, so I have the same thing. So this is my running on a VM. I'm not connected to a managed instance. You see the result is very fast. And this is on a VM, not a managed instance. And this will run till lunchtime. So that's the end of the section. So I'm here till the end of the session. Feel free to come to me, talk about databases. If you are looking for anything that you want to do or innovate with databases, feel free to come. And that's it from my side. Thanks a lot, folks.